Okay, so what we have learned was three components in conversion of analog signal to digital, which was sampling and then quantization and then encoding. Waveform codings, there are some methods that will try to do these three steps all together. So waveform coding is the process of converting a waveform directly into binary streams. So we won't have time to cover all of them, so we'll have some examples. One of them is pulse code modulation, which is you take your signal, you do sampling, then you do quantization, and then you do encoding. So PCM is used in telephony system. For instance, for telephony, your signal is first filtered, the bandwidth is less than 4 kilohertz, sampling is at 8 kilohertz, quantization will allocate equivalent to 8 bits, and encoder will convert them into a stream of data. Another method which is slightly more efficient is called differential pulse code modulation, which is used in telephony systems. This differential pulse code modulation, your input samples is first the difference between input and then one step prediction of input is quantized. So instead of quantizing the input, you quantize the component of the input which you cannot predict. So using the past samples, past quantized samples, we try to predict these xn. So basically this block here is one step prediction. So this signal here, this is x hat n. And because if this prediction gives you a good value, roughly close to xn, the difference, which is y of n, which is equal to x of n minus x hat of n, this is much smaller. So therefore, you're quantizing a signal which has less range, and then it is equivalent to have better performance. So you quantize yn, so y hat n. So the receiver uses these. So this is the error between the prediction. So this receiver, what it does, it gets this block. So it gives you exactly this block from this point to this point is the receiver. So if you have x hat n, you predict it and then add it, the error, you get the same signal. So if you look at here, this is y hat n, you add it to x hat n, so this is y hat prime n, this signal y hat prime n is equal to this signal, which I call it because this is x hat n is equal to x hat n plus y hat n. Okay, and then this goes to this prediction. So how this predictor is designed, usually they design an adaptive filter, an intelligent system. Sometimes they do some trivial and which works much better. For instance, for audio signals, DPCM using 32 kilobits per second gives you equivalent to 64 kilobits per second. So the quality of DPCM for audio using 32 kilobits per second is equivalent roughly to 64 kilobits. So almost half of bits and almost same performance. And 64 kilobits, slightly better performance, but half of data. So it's kind of lots of improvement. Another waveform coding as example is delta modulation. So delta modulation works very simple. So it's a binary stream. So and usually you compare. So you have your input signal, and then you compare it with some waveform reconstruction. So if you look at this is your input blue curve, and then compare it with the previous level. So my previous level here is this one, and then my waveform is bigger than that. So I get 1. Then I go to the next level. And because your input is bigger than output, so this is input. And this staircase function is the output. Because the input is still bigger than in, I get another step up because input is still big. So I go each time one step up. since my input is bigger. But at this point, the output is bigger than input, so I get -1. I get -1, and then -1. I continue -1, and this tries to track the signal. -1. At each clock, I get -1. At this point, the output is bigger, so I get +1. Then this one you get -1. Then +1, -1, +1, -1, +1, -1, +1. This is the sampling time. If sampling time Ts is a small, if is small, then I will have more levels and I could track the signal. Provided that delta, step size, if delta is small. So by reducing Ts and delta, you could accurately track your analog input. So this is called delta modulation. The disadvantage is that if you reduce Ts, this means that you will produce more bits. Okay, so this is called delta modulation. So delta modulation at each time compares the input signal, the difference between input signal and the output. You calculate, so this is your error. So the difference between the blue curve and this one, the input and output, and then you quantize it. And the quantized value is either +1 and -1. So it's 1-bit quantizer. You compare the input and output. If the input is bigger than output, you get +1. If it is not, you get -1. But this +-1 goes to an integrator. This is an integrator. Okay, because either I go 1 delta up or I go 1 delta down. So if En is +1, I go with amount of delta up. You multiply these +-1 by delta, and then you integrate it. And the receiver is nothing more than, this is the same thing. This integrator here is also your receiver. So you multiply it by delta and then integrate it. So this is also an integrator. So this is delta modulation. Sometimes in this curve you see that if the slope of input signal is very high, then this staircase signal cannot track it. So you will have a slope overload. So in order to eliminate this slope overload, either you have to reduce Ts or you have to increase delta. And both will create more bits, which we don't like. Another phenomenon which we see here is that we have a noise here around this area. If your signal is not changing with time, still you are going to have ± delta or something around that, because it goes ± around that point. So this is a noise. So in order to reduce this one, either you have to reduce delta or increase Ts, which requires more bits. As a remedy for these, some people, they will say, I will control the value of delta adaptively. I don't want to increase Fs because the receiver doesn't know if you increase your sampling frequency, and also your system may have a constant clock. So you don't want to change your sampling period. But a value of delta, you could increase it or reduce it. For instance, change in delta is adaptive, and the receiver follows the same protocol as the transmitter. For example, you can say that successively 3 of the outputs or more of the outputs, they have the same sign. I could increase delta by multiplying it by 1 plus alpha, and alpha is a percentage of increase. So for instance, you could double delta. If 3 bits are successively equal to +1 or -1, if they have same sign, if the output bits do not change 3 times successively, this is just an example, you could increase your delta. Or if your output bits do not change 3 times successively, you could reduce it. And if none of these two applies, you could keep it constant. So, and then the receiver has the same bits. Because the receiver has the same bits, the receiver also could update delta with the same rule and then do the same protocol and track the signal.